All right, so this video wasn't actually particularly wasn't intended, but I mentioned in the last video that, well, what did we do in the last video? We proved some characterization of what it meant to be an ordinal as if and only if, well, you're a transitive set of transitive sets, and that epsilon relation is total. So last time, what did we prove? We proved that, say, alpha is an ordinal. Alpha is an ordinal if and only if what is true? If and only if, well, alpha is transitive. All of alpha's elements are transitive. So maybe for all beta and alpha, beta is transitive. And then this final condition was that this ordering is total. So what does this mean? If we have two elements, they're either equal or one's an element of the other, or vice versa. And I mentioned that actually only 1 and 2 are necessary. So I didn't know if I wanted to give this, but I decided I think it's a nice argument, so maybe we can walk through the argument. So what we're going to prove in this video is that proposition is that, well, alpha is an ordinal if and only if this, but if and only if, so alpha is an ordinal. If and only if what? Well, if and only if alpha is transitive, and every element of alpha is also transitive. Okay, so this proof does rely on the axiom of foundation, and so maybe it's good just for this argument to actually state it. In the beginning, foundation tends not, for a lot of these videos that we're going to be the material that we're going to cover, we're not really going to use foundation. Foundation becomes more important as you take more advanced set theory courses, or if you're interested in graduate work in set theory. And so because it doesn't come up too frequently, I don't know, I think it's interesting to mention where it maybe comes up. So what does foundation say? So the axiom of foundation, or regularity is maybe the other name for it, foundation. What does it say? Well, it says that if you have some non-empty set, so for every non-empty set, right like this. So for every S, so if S is non-empty, so if we have any non-empty set, what does foundation give us? Well, then we know that there is some element. So there's what's called an epsilon, a minimal element. So in other words, there's some element X that's in S, such that for everything else in S, it's not the case that Y is an element of X. And if we're thinking about epsilon as less than, or some type of ordering, what this is saying is that there are no other elements in S that are less than X. So I think the way that we classified this when we talked about it originally is that all sets start from somewhere, is I think maybe what I wrote down. But another way to think about this is that the epsilon relation is what's called well-founded. Right? One of the implications of this is that there's no kind of infinite descending epsilon chains. So this epsilon ordering, epsilon is well-founded. And so maybe why to think about like why we're actually going to need this axiom to prove this result is, well, and I guess we also needed it here to prove this one, is, well, if we just have a linear order that is well founded, you can prove, I guess, that it would actually be a well ordering. So maybe that's what's happening. Okay, but what's the proof of this proposition? So we're going to use this axiom of foundation. So what's the proof of this What's the proof of this result? Well, we actually only need to show, well, if it's an ordinal, well, we've already demonstrated 1 and 2, right, because it's equivalent to this characterization up here. The only thing we need to show is that if we assume 1 and 2, we can actually argue that, well, if 1 and 2 implies that that relation is total, then we're done. So assume that 1 and 2 hold for alpha. And well, what do we need to prove? It's enough to show that this relation is total. So it's enough to show that this relation is total. And one way to do this is to proceed by contradiction. So assume otherwise. So assume otherwise. And maybe to kind of give a definition that we'll use just to make the definitions that we're going to give in the future a little bit clearer, we'll give this definition and say that if we have two elements of alpha, so maybe gamma and beta are in alpha, maybe we can say that they're comparable. So these are comparable. Well, if either gamma is an element of beta, or they're equal, or vice versa. So if either gamma is an element of beta, or gamma is equal to beta, or beta is an element of gamma. And so what does it mean to be total ordering? It means that all elements of alpha are comparable. So if we're assuming otherwise, it means that there are two elements that are not comparable. So what do we have? Since we're assuming otherwise, there's some alpha and there's some gamma and there's some beta, both in alpha, such that gamma and beta are not comparable. So in other words, they're not the same, and it's not the case that gamma is in beta or vice versa. And so this is when we're going to start appealing to foundation. What we can say is, what we're going to do is, let's consider this. Consider this set. So consider the set. So, well, if we just think about what alpha is, it's a set. And well, if we take any element, well, it might be the case that there are some other element for which it's not comparable. So in other words, it's kind of helping witness the statement that it's not true that we're total. So in other words, maybe I'll just write it down. So let's consider this at S, which is maybe all of the gamma in alpha. Such that there is something, maybe some beta in alpha, such that gamma and beta are not comparable. Okay, so what is this set doing? Well, if we just think about alpha, if this set is empty, so in other words, if this set is empty, well, then alpha would actually be total, right? Because, well, if this set's empty, that means for every single element of alpha, well, if you take any other element of alpha, or including itself, well, it would be that they're comparable with each other. But that's exactly what it means to be total. So this set is non-empty. And I guess further, what is it doing? We're kind of collecting all of the elements of alpha that kind of witness, that help witness that alpha is not total. And this is going to help lead to a contradiction. And the reason why is, well, now we can appeal to foundation. So by foundation. So by the axiom of foundation. So by foundation. What do we know? We know that there's some element, maybe we'll call it gamma, so maybe we're abusing notation a little bit, but there's some gamma that's in S, such that, well, for everything else that's less than it, so maybe for every theta, actually maybe writing it out with this notation, so that there's some gamma in S, so that for every other theta in S, it's not the case that theta is an element of gamma. So I'm just writing out what the axiom of foundation says, so the axiom of foundation is right here. I'm just writing out foundation, but instead of with x and y, we're using gamma and theta. So in other words, there's some epsilon minimal element of S. But what's going to be useful for us is this contrapositive of this part of the statement. So note what do we get from this? Well, for every single element in gamma, right like this, for any theta that's in gamma, well, it must then be the case that theta is not an S. We have that theta is not an S. But we can actually say something a little bit stronger, right? We know, well, we actually know further that, so to not be an S means what? It means that you're either not an alpha, right? Because this S is all the things in alpha that satisfy something, or you're comparable with every element of alpha. But theta is actually an element of alpha. So, yeah, right like this. Since theta is an element of alpha. Now, why is this true? It's because it's because alpha is a transitive set, right? We know that gamma is an element of alpha, right? Because by foundation and by the definition of S, gamma is an alpha. So that means that gamma is a subset of alpha, right? We're assuming that alpha is transitive. And so this implies that theta is actually an alpha. Well, since theta is an element of alpha, what has to be the case is that for every single element, say beta, in alpha, theta and beta are comparable. So in other words, not only is kind of theta witnessing that alpha is not total, all of its elements don't witness that alpha is not total. So all of gamma's elements are comparable with all of alpha's elements. Okay. So we're not exactly done yet, but we have to make one more, I guess there's one more kind of step to this argument before we kind of can start like finishing things off. What is that? Well, what do we have access to now? Well, we have access to this gamma that's in S that is minimal. It's epsilon minimal. Well, what we also know, maybe we'll call this S gamma. What is this going to be? This is going to be all of the beta that are in alpha. That, okay, so what has to happen? If we consider this at S, because gamma is in S, there is something in beta. There's something in alpha so that gamma and beta are not comparable. And so what we're going to look at now is that this is just all of the possible kind of choices that we had in this statement right here. So in other words, what's S gamma going to be? That's going to be all of the beta so that gamma and beta are not comparable. And this set is non-empty. Why is this set non-empty? Well, exactly because gamma is in S. And so what we can do is appeal to foundation again, right? So by foundation, what do we know? Well, by foundation, there's some, say, beta that's in S gamma, so that for every single theta in S gamma, well, we have that theta is not an element of beta. Right, just by writing out what does it mean, what does foundation mean in this case? Well, S gamma has some epsilon minimal element. So in other words, there's some element beta in S gamma so that everything else in it is not less than beta. But less than for us just means is an element of. And just like before, we can write this backwards, where another way to write this is, well, if we take some element of beta, well, it's also going to be in alpha for the same reason that every element of gamma is in alpha. And so what this implies is that if we take any element of beta, it would have to be the case that gamma and theta are comparable. So gamma and theta are comparable. And then what's one final kind of note, or just or just by the definitions of these things, gamma and beta are not comparable. So note. Gamma and beta are not comparable. So what's going to be the contradiction? We're going to prove that they're actually equal to each other, right? And so this would contradict that they're not comparable with each other. So what's the claim now? Maybe we'll do claim 1. Claim 1 is that, well, gamma is a subset of beta. So we're going to prove that they're equal, and we're going to do this by arguing that they're subsets of each other. The arguments for both are essentially the same. But this first step, how does it work? Let's assume that we have some theta that's in, so assume that we have some theta that's in gamma. And what we need to prove is that theta is actually in beta. So our goal is to show that theta is in beta. This is our goal. Now, what can we say? Well, what can we say? Well, what do we know about gamma, right? By definition, gamma is the epsilon minimal element of S, right? So by definition, gamma is in S, and every other element of gamma is not in S. So what we have is, well, if we assume that we have some theta in gamma, it must be that, well, theta is in S. So what does this tell us? Well, if theta is in S, it must be the case then that, theta is not in S. Theta is not in S. And, well, what does it mean to be not in S? It means that you're comparable with every element of alpha. So we can say, well, further, since beta is an element of alpha, right? Beta is an element of S gamma. We're kind of fixing beta. And, well, it's an element of alpha. And since theta is not in S, it must mean that theta and beta are comparable. So theta and beta are comparable. And so there are 3 options. Well, the first option would be that they're equal to each other, but this one's going to be impossible. Why is this impossible? Well, if beta and theta were equal to each other, well, it would be that beta is an element of gamma. But what's the problem there? By definition, beta is not comparable with gamma. So impossible. This is impossible. Impossible. Since beta would then be an element of gamma, this implies that beta and gamma are comparable. So this is a contradiction. Okay, so we can't be in this case. Well, what's the next case? That's impossible. The next case would be that beta is an element of alpha. But why is this impossible? This is impossible exactly because all of alpha's elements are transitive. So in other words, what would this imply? Well, we know that gamma is transitive because by our assumption, not only is alpha transitive, all of alpha's elements are transitive. So gamma is transitive. What does this imply? This implies that beta is in gamma. But this is impossible for the same reason as case 1. Right, because this would imply that beta and gamma are comparable, but by definition, beta is in S gamma, and so beta and gamma are comparable. And this last condition then has to be true. It would mean that theta is an element of beta. Well, that's what we wanted to show, right? So then we'd be done. This is maybe the end of claim 1. What did we just argue? We just argued that gamma is a subset of beta. Every element of gamma must be in this third condition, or must be in this third case. So in other words, it has to be in beta. Okay. Well, what's claim 2 going to be? It's essentially the same argument, but, or maybe it is the same argument. We're going to argue here that beta is a subset of gamma. Right, so we're just doing the opposite. And what's the argument for this? Well, assume that we have some theta that's an element of beta. Well, because beta is in S gamma, since beta is in S gamma, and well, beta is the epsilon minimal element of S gamma, it must be that theta is not in S gamma. So we know that theta is not in S gamma. But what does it mean to not be in S gamma, right? Because we also know that theta is in alpha. It must be that, well, if we take any element of beta, it must be that gamma and theta are comparable. So it must be, so gamma and theta are comparable. Are comparable. Well, what's the issue? Well, we just go through the 3 steps and we get the same type of contradiction and kind of the same types of contradictions for all 3 of these cases. So in other words, the first situation, well, if gamma is equal to alpha, that would mean that gamma and beta are comparable with each other. The next thing we could say is, well, if gamma is an element of beta, or sorry, is an element of theta, well, this is a problem. Why? Well, because theta is in beta, and because beta is transitive, it would mean that gamma, so gamma, if we're assuming gamma is an element of theta, since theta is in beta, since beta is transitive, it would mean that gamma is in beta, but that would imply that gamma and beta are comparable again, so we can't have that. And so the last case, which would have to be true, is that theta is an element of gamma, but we'd be done in this case. Right? Because then we've just argued that every element of beta is an element of gamma. So then we're done. So gamma is equal to beta, which is a contradiction because we're assuming that these 2 things are not comparable. So a contradiction. A contradiction. Okay. And that's what we wanted to show, right? What did we just argue? We just argued that if we assume that this alpha was not total, well, then we got a contradiction. And again, interestingly, this uses foundation, right? Because foundation is this claim that epsilon is well-founded. Okay. All right, so I'll see everyone in the next video.